Now we're going to study about electromagnetic waves. First of all, what is the meaning of electromagnetic waves? Electromagnetic waves are the ones which have electric field and magnetic field together, and they move together perpendicular to each other. So if suppose that if the electric field is moving in this plane and it's moving along this direction, then the magnetic field will be on a plane perpendicular to this plane, and it will look something like this. So if the electric field is in this direction, so let us say if this is electric field, then the magnetic field is along this direction. So it means that if electric field is in this plane, magnetic field is in this plane, so they are perpendicular. So electric field will move along this axis, along this plane, and the magnetic field will move along this plane like this. So it will look something like this if I draw it in 2 dimensions. So this will be magnetic field, and the electric field will be along XY plane. Okay. So now let's try to find a wave equation for it, and then we are going to find out the solution for electromagnetic waves. So in this entire video, what I'm going to do is, first of all, we are going to find out what is a wave equation for electric field and magnetic field, and then we are going to also find out the solution for the wave equation. But if you know that any general wave equation is given by curly square y upon curly x square is equal to 1 upon v square curly square y upon curly t square. If there is a wave and it has a function, wave function y, which is a function of x and t, and it is moving with a velocity v. Okay, this is a general wave equation. So we are going to find out wave equation for electromagnetic waves, and this equation, wave equation, any general wave equation, has a solution which is y is equal to y max sine of kx minus omega t. Sine of kx minus omega t or cosine of kx minus omega t doesn't matter, because in actual it is actually an exponential function, so it will contain sine also and cosine also. So this is what we are going to find out for electromagnetic waves. So in order to find this, let's take first of all Maxwell's equations, which are the fundamental equations for electromagnetic waves. So the first Maxwell equation would be Gauss's law, and Gauss's law is given by integral of E vector dot dA vector is equal to q upon epsilon naught. Gauss's law for magnetism is given by B vector dot dA vector is equal to 0. Then the third is Faraday's law, which is integral of E vector dot ds vector is equal to epsilon is equal to minus d phi b upon dt. Okay, and then the fourth one is Ampere-Maxwell's law, which is integral of B vector dot ds vector will be equal to mu naught I plus mu naught epsilon naught d phi e upon dt. Now, in order to make the problem easy, what we assume is that we are working in a space which is a free space. So free space will mean that there are no charges, so charge will be equal to 0. And if there are no charges, it means that dq upon dt will be equal to 0, or current will also be equal to 0. So these equations actually turn out to be then, the first one will be E vector dot dA vector must equal to 0. The second one will be B vector dot dA vector must equal to 0. The third one, which is this, will be E vector dot ds vector is equal to minus d phi b upon dt. And the fourth one, which is this equation, it will turn out to be integral of b vector dot ds vector will be equal to mu naught epsilon naught d phi e upon dt. Now in this equation, current will be 0 because this is what we've assumed. So this equation will turn out to be this. Now we will be using these equations and we'll try to find out the wave equation. Now if we see these equations, we see that this is a area surface integral. So we'll take area over the volume. This is also a surface integral, while this integral is a line integral. So we'll have to consider a loop for it. This is also a line integral because it is over length. Okay, while these two integrals, they are over area. So we'll have to take a surface area integral for this. So in order to prove these equations, we are going to consider some areas and we are going to prove these equations right. And from there we'll find out the wave equation. So we'll consider, for these two, we will have to consider a volume. And for these two, we'll have to consider a loop. So in order to consider a volume, the easiest volume that we can take will be a cube. So we'll consider a volume for these two and we'll try to find out. We'll try to verify these equations. And for a loop, actually, we'll take a few loops. Let's say if the loop is here, then what will happen? Let's say if the loop is here, then what will happen? Or if the loop is here, then what equations we'll get? So we'll take all these three loops and we'll try to use these equations to find the wave equation. So let us first start with a cube and let us try to use this equation and see what happens. Now, before starting with this, we'll have to consider a few things. We'll have to assume that the electric field and the magnetic field are in a particular directions. So we assume that electric field is along the y-axis and the magnetic field is along the z-axis, and they are constant. Electric field is constant along y-axis and magnetic field is constant along z-axis, but they will vary with x and time. So they are constant along y, but electric field, it will vary with x, the function of x and t. Similarly, magnetic field is also a function of x and t. Now what does this mean? It means that they will have in the YZ plane, the electric field and magnetic field will be constant, while if you move from and if you move in the x-axis, the electric field will vary. So let us try to draw this assumption. So the electric field is only along, so if this is x, this is y, and this is z, so electric field is along the y-axis and it is a function of x and t. So it means that at a particular y it will have a constant value, but if you change y, suppose if you are here or here or here, suppose that we need to find out what is the electric field here. So if at this point it is, or suppose if at this point it is x comma t, then at this point electric field will be x plus dx comma t. Similarly, we are saying that the magnetic field will be constant along z-axis. So let's say it will be bz and it is a function of x and t. So now let's say at this point this will be the magnetic field and it will be x plus dx comma t. Now this distance, it means should be dx. So if this is x, so this will be x plus dx. So ey function of x and t, ey x plus dx and t. Bz, if it is xt here, it will be x plus dx and t here. So it means that if we move in this plane, then electric field and magnetic field will change. But if you stay at a point, it is constant. So at this particular point, it will be constant. Electric field will be constant. Magnetic field will be constant. Okay. So now let us say that we try to take the first equation and let us say that we take a cube let us say this is the cube we are talking about and the electric field is in this direction, magnetic field is in this direction. So if you see, let's say that if we are proving it for E vector dot dA vector is equal to, we want to prove this. Now the electric field is in this direction, so electric field will be entering from this side and it will be going out from the other side. So the net flux from this cube will be equal to 0 because all the lines that are passing, they are passing through this area. So the net flux, electric flux will be 0. So it means that this equation is valid on this cube. Similarly, if we have B vector dot dA vector is equal to 0, then the magnetic field, it is in the z-axis. So the magnetic field is perpendicular to the area and it is entering from this side and it is leaving from this side. So it's entering from this side, it's leaving from this side, it's entering from this side and leaving from this side. So now this is actually magnetic flux, integral of, I can also write it as integral of d phi b. So the total flux through this cube will be 0 because the total number of lines that are entering are equal to the total number of lines that are leaving. So the total flux will be equal to 0. So this is not very difficult to understand.